Okay, I think we can get started again. Okay. Hello, my name is Brandon Mayer. I'm a software engineer at Google Research within the Algorithms and Optimization group. My work centers around graph building, clustering, graph embeddings, GNNs, and the general infrastructure to support these solutions for huge data sets that we encounter at Google. In this talk, I'll pivot away from some of the specifics of graph neural networks and TF-GNN library specifics to the ideas, the techniques and tools that we use to scale our solutions at Google, and introduce how these concepts can be applied to large-scale systems using Google Cloud and open source frameworks. I'll cover some common ML architectures focusing on problems that lend themselves to batch processing and how we accelerate and scale graph neural networks in this case. I'll introduce concepts from distributed data processing frameworks, notably Beam and Vertex AI, and reinforce the discussion with a walkthrough of Vertex AI, a hosted Python Jupyter environment that can interact with and orchestrate Google Cloud services and APIs. There's a lot of material that I'll cover and I'll move quickly, so the goal is not that you walk out of here knowing exactly how to deploy a solution, unlike the goal of Sammy and Neslihan before me, but maybe just so that you know some of the basic concepts that I've spent some time thinking about, and hopefully you'll have some areas you'll want to explore further as well. Broadly speaking, there are three different types of architectures to consider when scaling an ML pipeline, or specifically a GNN solution. There are so-called batch systems where large amounts of data are dumped or aggregated periodically to permanent storage, and we want to run training and inference in mass. Latency, as defined as the time between the arrival of the input data and the production of a prediction, is typically not an issue in this case, so long as our training and inference stages finish within a predetermined window of time, which is typically on the order of hours. A concrete example may be a system that periodically delivers aggregated financial or transaction information at certain intervals. We want to run anomaly detection or node classification for post hoc analysis. The second case we can consider is, we call it a dynamic pipeline. In this case, data is constantly streaming into a larger data store, manipulating the underlying statistics of a potentially larger data set. Training and model updating can still be run periodically, and prediction latency may or may not be an issue, but we'll want to retrain or fine-tune the model according to a schedule. Finally, we consider what we call the online setting. Latency in this case, again, defined as the time between the arrival of a new data point and a new prediction, is a key consideration. Graph data may be streaming in real time, and we need to run inference with minimal latency. Examples may include an OCR system on a mobile device for character or stroke classification. But for this tutorial, we'll focus on the batch setting and talk about ways of how to scale up the TF-GNN pipelines to graphs and feature sets that cannot be reasonably represented on a single machine or device. The batch setting is typically the easiest to scale to large problems using commodity hardware. Shown above is a typical architecture in the batch setting. As an example, the TF-GNN modeling pipeline takes a stream of TensorFlow primitives that are used to optimize a model's objective. In the batch setting, we're not very concerned with the latency between the arrival of new data and the production of a label, but can instead concentrate on processing throughput. This allows us to split up the pipeline into scalable, sequential components. Graph subsampling has been used successfully to train GNN models at scale, and it helps break down a graph that may not fit onto a single machine into smaller graphs that we can easily handle with minimal side effects. The output of the graph subsampling pipeline is a database of TF examples that can be used to feed a TF-GNN model. Graph subsampling at scale is a challenging problem of its own, and we'll touch on that a little bit later in the talk. Once graph subsampling is complete, we'll need to stream data into a training process. Typically, when training with hardware accelerators, the models may execute training steps so quickly that having a single processor machine reading, parsing, and pre-processing the output of the graph sampler can't keep up. In practice, we typically employ TensorFlow abstractions, namely the TF-data object and the TF-data service, to scale reading, parsing, and preprocessing over a cluster of machines to achieve high throughput. Finally, TF-GNN has native support for TF distribution strategies, another TensorFlow abstraction that allows us to scale and orchestrate training logic from a single CPU to clusters of machines or hardware accelerators using GPUs and TPUs. This enables high throughput training that is extremely useful for scaling batch ML pipelines. This figure visualizes the process of graph subsampling at scale, showing a one-hop neighborhood extraction centered around a set of seed nodes. The graph subsampling algorithm we consider will take as input a list of seed nodes, a user-specified list of nodes considered as targets or graph centers, and expand in a breadth-first manner from each seed according to a user-specified sampling plan that we call the sampling spec. Real pipelines will typically want to subsample n-hop neighborhoods, but it's just easy to visualize the one-hop case. And to reiterate, we're considering the case where the full graph, including features, is so large it cannot fit into memory on a single machine. Graph subsampling would not only be trivial if the graph could fit into memory, but probably unnecessary by definition. We take as input a graph complete with adjacency data and potentially node and edge features specified in the Unigraph format that was kind of covered in the last two talks. It's a format defined by the TF-GNN library, and we'll cover it again in a little bit more detail in some future slides. In the heterogeneous case, there are many ways that a graph can be subsampled, including completely at random, but in practice, it's best, we find, if a modeler comes with a plan, a domain-specific expression of traversing the graph structure that may be advantageous to modeling. For example, an expert may know a priori a graph traversal plan that captures features and data that is important to the subproblem they are trying to solve. So we'll look at a couple of approaches for graph subsampling. Broadly speaking, again, we can break down these approaches into a couple of buckets. Graph compression can be used to create a representation that can potentially shrink a very large graph and fit it onto a single machine, perhaps in a lossy or lossless manner, at which point we can leverage traditional compute resources to process the graph. Of course, the downsides of this approach is that compression ratios may be dependent on the topology of the graph, and a feasible solution may not generalize. It might introduce additional delay into the overall pipeline or loss due to compression in the downstream sampling procedure. Graph partitioning can be used to break a large graph into multiple overlapping pieces that can then fit on a single machine. The partitioning should include enough padding so that the problem of subsampling can be independently solved on each machine without loss of information. This might be difficult or infeasible to do for certain graphs, and additionally may not be worth the effort compared to perhaps other techniques. Distributed techniques leverage storage or compute paradigms that shard the graph representation over multiple machines and delegate work to pools of machines that are coordinated in some fashion. On the storage side, graph databases may offer large-scale solutions and give the user control to trade off latency and bandwidth considerations through some scaling parameters. In-memory distributed systems can also be leveraged to create fast key value stores that can be used to represent adjacency information and support fast association between node and edge IDs and feature sets to further scale the processing time of subgraph sampling. Distributed data processing techniques such as Apache Beam or Spark provide a consistent SDK for handling distributed data processing and the representation of graph topology and features. Google has enjoyed a lot of success scaling algorithms to commodity hardware using data flow processing paradigms. So we'll focus on some ideas from that field. An even more performant solution may use techniques from all three, but in this tutorial, we'll just focus on the data flow style approach. We'll show the basics of implementing a pipeline using an SDK of operations that can be automatically optimized and sharded across a pool of cheap commodity machines for graph subsampling. And this has the advantage of scaling while minimizing cost. No special hardware or large memory capacity machines are required. And the downside is that these algorithms can be difficult to express optimally in the data flow pipeline. Yes?
So what if you cannot compress the graph? So you use the functionality of if it is like, for example, a protein,
Mhm.
so how do you want to partition or make it subsampling?
Yeah, this is, so I'm proposing here that that is exactly the problem that I'm trying to avoid. The compression or partitioning methods may induce loss, or you might have a suboptimal representation. So we're going to look at this distributed technique that allows us to, without any loss, represent a huge graph over multiple machines and then use the data flow SDK, or it's a sort of MapReduce style computation to subsample the graph without any loss. There are trade-offs, of course, like with Sammy's in-memory sampler, he can learn a sampling function and he can generate samples on the fly according to how a model is performing. In the batch pipeline case, if you create a dedicated process that is doing this, you're just going to get whatever set of samples you have, and then you'll shuffle and iterate over them during training. That's why we're going to focus on this technique, and it usually gets us very far. And so this slide summarizes the system architecture of a sampling pipeline written in Apache Beam using TF-GNN. It's just, you shouldn't know the specifics of it, but it's useful to keep in mind as we explore the algorithm. And we'll touch on each part of the components, and you can think of as like a vertical column in this slide. We noted that we defined the Unigraph format in TF-GNN to read graphs from a number of common storage solutions and represent the graph data using Apache Beam objects, specifically P collections and P tables, which I'll talk about in another slide. The Unigraph API accepts a user specification of the graph topology and data locations via the graph schema specification, which you can see here in the yellow box. The yellow boxes are any user supplied configuration files. Give another user-defined object that we'll call a sampling specification, which is, again, just a user's plan of how to traverse and subsample the larger graph. We'll read the graph into Apache Beam via Unigraph. We'll implement the subsampling procedure, which will produce a stream of graph subsamples that can be written to cloud storage in a format that can be immediately consumed downstream by a TF-GNN training pipeline. So let's take a closer look at the Unigraph protocol to understand how data will be fed into the graph subsampling pipeline. Neslihan and Sammy talked a lot about protocol buffers, and we do that a lot at Google. There are a lot of jokes about that, but Unigraph is another text-centric protocol buffer that defines a heterogeneous graph. In the following slide, we'll keep a visualization of a toy graph on the left, an example of the relevant graph piece that would be defined within a larger Unigraph protocol buffer message on the right. In this example, we consider a citation network similar to the familiar OGBN MAG dataset, which I think Neslihan had a slide about, except that in our example, there are only two types of nodes, just authors and papers, let's say, and two types of edge sets, maybe cites and writes, that connect the nodes within the node sets. With Unigraph, we define a couple of objects. First, the node sets, as we've said before, which is a specification of a type of node with an ID, and potentially with features that we represent as TensorFlow example in Protos. Edge sets are the adjacency information that specify links between individual nodes in the node set. Edges can also be associated with edge features as expressed with TensorFlow examples, as we've said before. We've also touched on the fact that we can express a global context feature for a graph or any subsample of the graph. And there's also some metadata that actually includes the location of the underlying data, where the nodes live and what format their information is stored in. So you can think of this like graph piece as a template, a message telling the program there's going to be some data living somewhere, and it will look like this. The node set submessage for the graph schema is shown above for the authors node set, which defines this template. In this case, authors merely specifies a string ID field and the location where the data lives. In this case, a sharded TF records file. Similarly, a paper node set has a unique string ID, but it also contains a 128 vector of floating point numbers, which presumably is an embedding representation of the paper's content. Now that the node sets are specified along with their features, we can express the adjacency information or the links between the nodes as edge sets. Shown here is an example of the cites relation, a mapping from papers back onto the papers node set. In this case, the edges are directed relationships, mapping papers to other papers that presumably they cite. The right's edge set similarly defines a set of edges mapping from author IDs back to paper IDs. And then we can go ahead and define something that's slightly more interesting called a written edge set. Not only does it define edges from papers to authors, but the data doesn't explicitly exist. We just use an extra metadata field to define a reversed property. That is, the edge set is just the reverse of the rights data source. And this is just as simple as swapping the source and target values in the downstream representation of the edge set. Okay, so we covered a simple graph schema, and we touched a little bit on what a sampling specification is. It's just a plan on how to traverse a graph. And we have a graph schema, but let's say we need a sampling plan. As usual, we encode the plan as a protocol buffer, which we call the sampling spec, or sampling specification. The sampling spec defines this traversal plan that enumerates the parts of the graph that we'll visit. They have to be defined in the graph schema, and the edge sets that we'll traverse in what order, and the sampling parameters that are necessary to apply to each piece of the graph. The image to the left is, the image to the left is a graph plate notation of a sampling specification for the OGBN mag dataset, which is shown in part as the protobuf text format that's on the right, at least in part. The message states that we define a seed op named seeds that consists of every node in the paper node set. For each paper node, we sample more papers through the sites relation, which defined a paper-to-paper link sampling 32 cited papers using a random uniform sampler. Other sampling options include top K sampling or random weighted sampling, but top K is actually recommended for production systems to maintain determinism. The sampling spec typically allows modelers to encode their prior knowledge about what parts of the graph are important to the problem and how the original graph is structured. There are, of course, ways to learn and automate this, but in the batch setting, it's typically easiest to take an intuitive sampling strategy, and that will go a long way to making the pipeline simpler and taking less computation. So coming back to Apache Beam that we introduced in the system architecture slides, we'll cover some of the basics just in case you're unfamiliar. Apache Beam is an open source SDK that is available in many languages that defines a data flow, or sometimes people call it MapReduce style of computing. The top level abstractions of beams are pipelines and runners, which users define in order to run distributed computations in a particular environment. Beam pipelines define a computation DAG, a series of computations to be executed, while the beam backend that you choose via a runner specification will optimize and distribute the user-defined computations that you write in a pipeline. For example, there's a direct runner for running beam pipelines locally on a single machine. It's not suitable for production, but it's useful for testing. Alternatively, there are runners for executing pipelines on specific clusters or cloud services to achieve horizontal scalability across multiple machines. The Dataflow runner is the Apache Beam runner for executing pipelines on Google Cloud's Dataflow service, which we'll use in our tutorial later on using the Apache Beam SDK. We'll cover a little bit of the basic objects within Apache Beam, but a P collection is an Apache Beam object, which in the Python SDK represents a potentially large collection of objects. A P collection will not be materialized on a single machine, and is only an abstraction for representing a distributed or sharded data to be processed downstream by some sort of transform. A common misunderstanding is thinking that a P collection is a replacement for a Python list that can be iterated over, and it can't. The best way to think about it is a symbol that can be passed downstream to other transformations. The Beam engine will take care of processing and transforming P collections behind the scenes. As an example, the canonical operation in Beam to consider is the par_do, short for parallel do, which will apply a user-defined Python function independently to each item of a potentially huge P collection. On the Beam backend, the system will shard and distribute the P collection over multiple machines and then apply the input functor independently and in parallel on each element of the P collection. We need a couple of more primitive ideas within Apache Beam to represent a graph. And what we call a P table is merely a specialization of a P collection with key value semantics. Under the hood, P tables are merely P collections of tuples. In the same way P collections aren't replacements for lists, P tables are not representations for things like maps or dicts. You cannot iterate over them, and they do not support lookup operations. However, we can join and aggregate over their keys, similar to SQL. So coming back to graph subsampling, when we load a Unigraph for graph subsampling with Dataflow, we load each graph piece from its specific source, like a disk or a database, such as BigQuery, into Apache Beam as P tables keyed by node IDs. Each sampling op will come up with an adjacency list, a P collection of node ID to neighborhood pairs. Using this framework, a graph subsampling algorithm can be expressed as a series of joins and some additional accounting and pruning operations. Visualized above is a Beam's cogroup by key operation to join two tables in a distributed fashion by matching keys. The output table has a primitive implementation that has the primitive information that we would need to sample as part of the graph. And again, we can build a naive but scalable graph subsampling algorithm as a successive application of adjoins, pardos, and a little bit of accounting. We'll take a look at this later on in the tutorial, but this is a visualization of what our scalable graph subsampling DAG looks like when we visualize it in Google Cloud Dataflow. The top are the primitives defined by the Unigraph routines to read information from cloud storage solutions. Seeds and adjacency lists are created from the graph primitives, and samples are obtained by a slightly more sophisticated procedure than what I just described. In summary, we achieve state-of-the-art results using TF-GNN for batch production pipelines at scale following a few system design templates. Typically, a distributed compute pipeline ingests data from multiple sources, creating a graph that we can read via Unigraph. A distributed graph sampling program generates subgraphs according to a user-specified sampling specification, which is read into sharded permanent storage solution. To achieve the high throughput necessary for batch pipelines, we scale data ingestion and preprocessing using TF data service to instantiate a cluster of machines that will coordinate to generate and prefetch huge amounts of graph tensors from the output of the graph subsampling step. These are fed into models that are TF distribute aware. We can spawn up different hardware topologies, including CPU-based parameter server architectures, multi-GPU models, and variable TPU topologies. In the batch setting, it's typically trivial to load a saved model onto multiple machines using a distributed framework such as Dataflow and iterate over the eval split to generate target inferences that are placed on permanent storage to be pushed for